Hello, everyone, and welcome to today's webinar, High Performance Material Solutions for Frac Plugs and Casing Tools. My name is Mike Moran. I'm the Vice President of Engineering at the Gun Company, and I'll be your host today for today's session. First, I want to thank all of you for taking the time out of your busy schedule to attend this webinar. But before we begin today, I want to cover some basic housekeeping tips to maximize the value of your webinar. To ensure the best connection possible, please close out any programs or apps that might be eating up a lot of data in the background to free up your bandwidth space. If you experience any technical issues, please call the help desk support line at the number provided in the chat box. When you signed into the GoToWebinar app will default to your computer speaker and microphone system automatically. If you prefer to join over the phone, select telephone in the audio pane, and the dial-in information will be displayed. This will also help clear up some bandwidth. You will have the opportunity to submit text questions by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect all these and address them during the Q&A session at the end of today's presentation. If you prefer to ask us a question directly rather than type it, raise your hand and we can unmute you. Any unanswered questions will be followed up via email following the presentation. Today's webinar will be recorded and available on demand on our website, www.theguncompany.com/webinars, and a link will be sent out to all attendees following the webinar. So, without further delay, I would like to introduce Kyle Sylvester. Kyle has 10 years of experience in oil and gas downhole composite tool manufacturing. During that time, he has worked on multiple projects requiring downhole composites produced from a variety of composite materials. Before working with composites, Kyle worked for several years in production chemicals for Permian Basin and Eagle Ford. Kyle has a BA from Texas Tech University and an MBA from Texas State University. So, Kyle, over to you.
Thanks, Mike. Before we get started, we're having technical difficulties. I'm not Joshua Pajor. I'm Kyle Sylvester. So, wanted to thank everyone for joining us. Good morning, good afternoon, or good evening, wherever you are today. Thank you for your time. This is going to be an overview of composite materials used in your downhole tools, whether it's for frac or casing operations. I'll be covering the following agenda today to try and give everyone a brief overview of composite materials and how they are produced. We hope to give you some ideas on different composite options that you might not be as familiar with. Before we jump in, we wanted to take a quick poll to get a gauge on how much experience everyone has with composites, whether it's years or just getting started. Okay, the poll should pop up in your pane on the screen. If you wouldn't mind, take a second to vote. I'm going to give it about 3 more seconds, and we're going to close it out.
You get back to your presentation there. Stop sharing and then hit stop share. There we go. One second, folks, we'll bring it right back. There you go. Oh, now we got your notes. Flip that display setting. There we go.
Sorry about the delay, everyone. It looks like most of you are fairly new to composites, with over half of you having 0 to 5 years experience. First, let's get into a brief overview of what is needed exactly to make composite materials. In a nutshell, we need to add a reinforcement to a matrix. Matrix materials like thermoset plastic, thermoplastic, etc. are generally not very strong without a reinforcement added. There are seemingly endless combinations of reinforcements and matrices. Today, however, we'll be mainly focused on thermoset and thermoplastic composites. We know most of the applications you work with, you're interested in the mechanical and physical properties. Mechanical properties are highly influenced by the fiber content and the fiber orientation. Tensile is mostly driven by fiber, while compressive and shear are primarily affected by the matrix. Flexural, since it is a combination of tensile and compressive, can be affected by both fiber and matrix. Since you joined us today, you have access to our white paper on tensile strength. Please click on the link in the resource section. There's also additional papers available upon request in our technical resource library, so please reach out if you'd like to access those as well. Fiber orientation also has a direct correlation to nearly all mechanical properties. When designing your parts, optimizing fiber orientation needs to be taken into consideration. For example, random fiber mat is very inexpensive, but quasi-isotropic fabrics that provide fiber placed in 0, 90, plus 45, or minus 45 orientations can be very expensive. But the properties obtained by using them are nearly isotropic, hence the name quasi-isotropic. Based on this curve diagram, we would expect that the tensile properties transverse to the zero fiber orientation and would only be around 15% of the properties found at the zero direction. Random, bidirectional, and quasi-isotropic orientations should also provide about half to two-thirds of the tensile properties found in the zero orientation. A frac plug is a good example of parts utilizing different angles to improve certain property strengths. Even though you have components all going together on the full assembly, different parts utilizing different wind angles or fiber orientation depending upon each component's function. Now we are going to get into the many different ways to make composites. Some of the technologies, such as compression molding and hand layup, have been around for more than 100 years. Today, we are going to discuss several composite manufacturing methods that are common in downhole tools, and a few that are not regularly used. Before we dive in, we have our second poll today to see what composite most of you are working with for your tools. I believe the options that will show up in your pane are filament wound, convolute, molded, and sheet. If you would, we're about to launch the poll if you would take the time and vote. Give it about 5 more seconds here. And we'll close it.
About 1/3 molded and 2/3 filament wound in that.
Yep, it's about 67% filament wound, 33% molded, and I'm sure some of you utilize both with some of your hybrid plugs and tools. First, we'll start with probably one of the most popular composites for downhole tools that are made from compression mold. There are many benefits to compression mold. High property strengths with random fiber orientation allows for really high performance parts. There are many glass options and systems out there, literally thousands to choose from. With longer fiber systems, you can provide extra strength. Compression molding allows for a high part output, giving you select the right cavitation for your mold to meet your demand. Some of the disadvantages: although the longer fiber has benefits, it can be harder on the manufacturing process and add additional steps such as preforming materials. Another factor is also the tooling cost. Molds are typically a higher capital investment compared to other options. Not ideal for smaller production volume parts. With setup fees and run times, it can increase your part costs on smaller volumes. There can be limitations on part sizes. It would be hard to find a press and mold to produce larger parts you see in most casing tool sizes. say up to 13 3/8 inches up to 24 inches, but they are out there. And compression molding obviously works great on smaller parts. To continue on the topic of molding, next we'd like to look at injection molding. Your typical grades for injection molding are your polyamides, which would contain your nylon classes such as N6. Material is again glass fiber, although they are shorter fibers than those in compression molding. Same as compression molded, there are thousands of injection molded materials to choose from. Some of the advantages of injection molded parts are that they allow the highest production volume output of all the different composite manufacturing styles. That is due to the shorter cycle times, which leads to low-cost part pricing. Injection molding also allows for parts with complex details that you might not be able to achieve with compression molding. And thermoplastic parts are also the best option for parts needing flexibility and extensibility. Some of the disadvantages: with thermoplastics, you do not get the higher temperature mechanical property performance that you normally would with compression molding and filament wound parts. You can pay a premium for higher mechanical properties, though, with some of the exotic materials that are out there, but it's usually cost prohibitive. Again, like compression molding, the mold costs are going to be relatively high upfront costs to begin your project with. Even though there are disadvantages on some of the performance, it seems with injection molding, it has made the most technology breakthrough, and thermoplastic materials are getting better every year. Another popular option that many of you are familiar with or utilize would be filament wound composites. Epoxy resin is the most common use. Some of the advantages filament winding provide are strength of material, winding angle options to manipulate property performance, minimal lead time for tubes, low-cost tooling requirement, competitive part pricing, and no limitations on OD and ID dimensions. These can be ideal for large casing tool sizes up to 24 inches. In some of our other markets, we even wind ODs that are over 60 inches. Some of the disadvantages: you're primarily limited to glass filament and roving, such as a substrate, and also a limited range of resins. Machining finished parts can add to lead times for molding. Compared to molding, you can have a part completed in minutes, whereas some tubes will require over a day to cure. Parts have to have an ID, so you cannot produce a solid part. And also there's waste. Due to machining, you have material waste versus getting a net molded part. Here's a quick video of filament winding in action. The picture on the left is a 6-spindle winder. The center is a single spindle, and the one in the video is an 8-spindle winder. Notice the wind angles on the tube in the video are 45 degrees. Depending upon the forces seen on your tools, we can adjust to improve. Another type are high-pressure laminates, which many of you also know it as sheet materials. Most of you are familiar with G10 or G11, but there are other grades such as G3, G10, G12, and even G15. The differences are the glass transition between these grades. G10 is typically 155C, whereas G15 is 200C. Sheet can be made with phenolic and epoxy, silicone, and polyamide materials. Advantages for these are strength of material, high hoop, and compressive strength. They also allow for a large range for OD sizes. Many sheets come in 48 by 48 inches or even 60-inch dimensions, so they can handle your large OD parts. And there's also no tooling required. Some of the disadvantages: there are height restriction for your parts because of the thickness of the sheet. Usually the highest is typically up to 6 inches. Also, it's typically a higher part pricing. And you have limited property improvement options. Unlike random molded fibers and angles and filament wound parts, you cannot improve sheet. You're limited to 0 and 90 degrees in the fiber orientation, and there's no Z fiber. Another type of winding is convolute, where filament winding is utilizing several strands at once. Convolute tubes are made by wrapping a cloth sheet around a mandrel. The benefits to this is strong property strength and low tooling cost. Disadvantages: the raw tube and part pricing after machining are usually higher than molded and filament wound components. Also, if you're needing high volumes, the tube wrapping process can be longer than winding on an 8-spindle winder. Fiber orientation is limited to the glass cloth orientation that is being used. Pultrusion is a very good process for making rods, angles, and channels in high volumes. Typically, continuous fiber or fabric is pulled into a resin bath and into a heated die for curing. The pulling can be done by a tractor pull or a reciprocating puller. These short videos show the inlet and outlet of the pultrusion die. The first video here is showing the fiber going through the resin bath and into the die. The second video is showing the fiber coming out the die fully cured. The sound you're hearing in the background is actually the saw cutting the rods coming off the dies. Pultrusion tubes for rods and pins are probably the main uses in frac and casing tools. If you haven't seen the pultrusion process, I hope these videos were helpful to you.
And you get to see it again if you missed it the first time.
Another option you might not have as much experience with is VARDM. VARDM stands for Vacuum Assisted Resin Transfer Molding. It's a process that allows for custom molding with low-cost tooling. VARDM would be better for lower volume applications. How does it work? Fiber reinforcement of different types can be hand laid up into the A-side rigid mold and a vacuum bagged on the B side. The vacuum draws the resin through the fiber. The initial curing usually takes place at room temperature. After demolding, a post-cure can take place to further enhance the properties. This short video shows how the resin is pulled into the fiber using vacuum.
The reinforcement with little extra resin to just. All right, we've begun the infusion process at 418. As you can see, the resin has permeated through the green flow media and is in the fiberglass reinforcement and traveling down the reinforcement at a rapid pace. This is fiberglass that is designed for infusion through the vat. Vacuum pump is still on, as you can see, and here we are maintaining a vacuum pressure of about 29 inches of mercury. As you can see, our resin is now gelled at air temperature. It is 428, exactly 11 minutes after the resin was initiated.
Although it's not as common for oil and gas parts, it is an option, especially for your very large-sized tools. It is used quite a bit for aviation and aerospace, but we did want to show the process for those that might not be familiar with it. This table is intended as a summary of costs of what we reviewed and a few we did not go over. Sometimes some initial questions about volume and complexity can help rule out certain manufacturing techniques. High volume parts tend to require a higher capital investment for the tooling that's required. Now, with the introduction of additive manufacturing, prototype composites can be made for fit and function prior to making the investment into injection molding dies. It has been a huge benefit for many designers. Now that we've discussed all the manufacturing methods, let's review the different ways we can test and characterize composite materials. We have material test labs at 8 of our locations in 5 different countries. We have test fixtures for performing standard ASTM or ISO tests for tensile, compression, flex, and shear. In summary, we can do full material characterizations. Some examples include resin testing, physical properties like class transition temperatures, chemical analysis, and burnouts. We also make custom test fixtures for testing specific applications to predict the performance of composite in these applications. In addition to material testing, we can provide component testing for most frac and tank and casing tool applications. This can help speed up the R&D prototyping phase as we can produce parts and test on-site to help prove out a concept faster. We have the capability to do over 10 individual tests including all frac components and threaded parts. We have a hydrostatic pressure chamber, which allows us to put a full plug or tube into casing and pressure up on it until failure. We also have a heater chamber with a pressure pump that allows us to do full plug testing. This starts at a setting simulation and can take it to failure as well. Additional resources we have to help is our engineering team at the gun company. We have trained applications engineers with composites experience that can help identify the best product options for your tools. If you need a custom solution, our development engineers help design the composite and develop the prototypes for testing. Our labs are equipped with standard and custom test equipment for testing prototypes quickly. Our goal is to help you get the materials you need for your project to the market as fast as possible. That concludes the webinar portion. I'm going to turn it back to Mike for the Q&A.
All right. Thank you, Kyle, and thanks, everyone. We're going to begin to answer questions, and we've had a couple of them submitted before today's presentation, so we can start with those as everyone else begins to add their questions or raises their hand. And if you raise your hand, we can unmute you, so we'll be watching out for those that are raising their hands. Let's see, we've got a couple. We've got Li Zhao that's raising a hand right now. It looks like, yeah. Did I say that, Li Zhao?
Yeah, this is Li Zhao from CNPC USA. So may I ask a question about your the service? Do you guys model or you develop your own resin formulation by yourself?
So yeah, we have our own formulations. Are you talking about the molding compound?
Yes, we have some unique properties from the resin. So do you guys open to work on new resins?
Okay, yeah. Yes, we do have some of our own molding compounds and SMC compounds. I believe that's the question. And we also use some off-the-shelf compounds that are commonly used in the oil and gas business.
Okay, so for SMSC, do you buy this MSC compound from a compounder, or you guys prepare your own compound?
We do both. We have both. We will purchase some if a customer has a specific compound that they like to use. We will use that compound. And in some cases, we will actually have our own formula. Like, I don't know if you saw the G160 formula. That is our own formula and our own compound.
So you have this MSC machine in-house, and you can formulate the way you want?
Correct.
Okay, thank you. Appreciate it.
Mm-hmm. Yeah, thank you. Thank you, Mr. Chow. Okay, any other questions here? Hands up. Okay. We had another question come in during the, Kyle, we had someone ask, Kevin asked if the pultrusion rods are cured with heat or if it's just a room temperature cure.
The pultrusion rods, whenever they go through the die, that is where it's heated up and cured. So you might know a little bit more about what temperatures those are usually.
Yeah, there's different profiles for different resin systems, but usually, you know, the beginning of the die will actually have a lower temperature to begin the reaction, and then it'll change throughout the die of different temperature settings throughout the die. Okay, thank you for that question, Kevin. And also another question from another Kevin from before the presentation. Are convolute tubes stronger than filament wound tubes? Okay, that's pretty broad, but we'll probably try to tackle that.
Yeah, typically if you had, let's say you had a convolute tube and a filament wound tube side by side, same angles, convolute tube would allow for probably a little bit better property performance with ILSS and also compressive strength. I think with filament wound tubes, you can manipulate the angles to get pretty close to convolute tubes. But yeah, typically if you did it side by side, your convolute would give you a little bit better on the mechanical problem.
Yeah, I would tend to agree. You can get very, very close with filament winding to a convolute tube. The properties, I think the layers on a convolute tube are pretty concise and consistent, and that's what gives you the better performance. The filament winding, with a roving, you get some inconsistencies with the layers, and that's where you might find that there's going to be a little lower performance unless you have a very consistent winding pattern and you get close to that 45-45 winding pattern. Okay, let's see, any other questions? Just checking. We do have another one that came in from Tom. Let's see, Tom said he had a couple questions for us. Let's see, Tom asked, can Garolite G10, yeah, G10 is commonly referred to as Garolite. That's an old brand name that's been around. So can G10 composite material pass 5,000 psi hydro test? And can G10 be threaded for assembly onto a steel or aluminum component? So kind of tackling those, it sounds like that might be like a casing application, Tom, but not totally sure. But anyway, that for the threaded assembly for sure, yes.
Definitely.
Yeah, you can definitely thread G10. It's not a problem. It does pose some challenges if you don't have the right equipment. You got to have a pretty, depending on the size, you got to have a pretty sizable lathe or a good, the right cutting tools to do that.
And then also for quality, you want to make sure you've got a gauge that way whatever you're wanting to thread the G10 onto will mate up properly.
Mm-hmm. And I will say the type of thread makes a big difference a lot of times in your success. So, we've found that there's a lot of different thread types that are more successful with composites, and you can't just use your standard thread type in there.
And then I think also going to about the, I think getting over 5,000 PSI, I think depending on the design, I think definitely can, but a lot of it's going to depend upon the part density, what angles you're using, and what's the function of the part.
Yep. Okay, looks like we got another question from Chris. How do you maintain the mixture ratio when using fiber in a material matrix? Okay, basically, how do you ensure the fiber is distributed evenly throughout the mix? Okay, this sounds like maybe a good question for like a compound, compounding situation or an injection molding situation. You want me to try to tackle that one?
Yeah, sure. I mean, I think I was just going to add, a lot of the random fiber orientation would have a lot to do with it, and also the distribution of the resin.
So mixing the mixture ratio, okay. So it just depends on what we're doing there, but if we're talking about like a BMC for say a thermoset molded, compression molded material, typically the BMC you're weighing out the amount of fiber, and you're weighing all those ingredients, and you have the lost weight. You can have a lost weight feeder, and we weigh all those ingredients out, and then you blend all those ingredients together to make that BMC. If you're talking about SMC, there's also a feed rate factor. So if you're chopping and feeding the gun roving into the SMC machine, you have to feed that roving and the belt and everything that it's falling onto at the correct rate. Otherwise, you can end up with a fiber content problem. You get fiber content variation. I hope I answered that question correctly, Chris, and that answers what you're looking for.
Is there any other questions?
Yeah. Okay. Let's see. We had another one that came in earlier that. Let's see. We had a question about drill out time from Tom again, and one of those things is drill out time is one of those things that there's a lot of factors involved, and I will just say the main thing. There's a couple main factors there, and you asked about G10 material. One of the biggest thing, obviously, is the amount of material there. If you're talking about composite materials, it's just, how much material are you having to drill through, obviously. But if you're saying the same material, same amount of material, one material versus another material, in our experience, the two biggest factors on the composite are, one, how much fiber reinforcement are you placing into that material? And then two, what is the resin system that you're using? Is it a hard resin system or is it a softer resin system? So, of course, if you are trying to make a composite that goes for hotter and hotter wells, you have to have a higher temperature resin system. Higher temperature resin system means it's harder. It's probably more brittle, more hard, and you're going to sacrifice drill out time with that. If you have a well that doesn't get that hot, and you can bring the temperature of your resin system down, you're going to be getting into some softer resins. So you sacrifice. Essentially, your drill out time will get better if you use a little lower temperature resin. So I hope that answers your question, Tom. Let's see. Any other questions on here? While we're looking at some other questions here, we'll take one or two more questions. I know we're doing pretty good on time here. We're pretty efficient with everything. Just want to point out again to everybody that there are some handouts on the resource area here in the handouts area that you can download. The other thing I want to mention is that we do have two other similar white papers on mechanical properties. One is compressive strength, one is on flex strength, and there will be a fourth white paper coming out next week that we will be emailing to everyone that's on our email list. So if you're not on our email list and you want to get on our email list, let us know, because only people that are on our email list will get this handout. If you try to go to our website and get it, you will have to sign up to get the full version of it. So you cannot access these technical papers, the full version of those technical papers, unless you're signed up with us. Okay, got another question that came in from Mike. What is the max length for a filament wound tube or a convolute wound tube? What's the max length for a tube? So
I think just depending on the applications, there's even composite casing now, which those can be over 13 feet. I think that's probably about the highest in oil and gas. I think typically, just depending on the component, the weight, those, for frac plugs, those would be anywhere from 48 inches all the way to 90 inches. Obviously, you want to utilize as much of the winders as possible to increase your yield, but typical sizes on the low end, 48 inches to 90 inches.
Yeah, convolute is, I don't know if you answered this already, but the convolute tube is limited to how wide the fabric that you can weave. So, I mean, you can get some wide fabrics, and then you got to saturate that fabric with resin. But typically, you see that the convolute tubes are limited to like 50 inches wide. Filament wound, like Kyle said, I mean, we can make filament wound tubes that are up to 20 foot long.
Yeah, and even some of the composite tank applications you see, I mean, those have 20 foot ODs.
So yeah, I mean, it's not a problem to have even larger convolute or larger filament wound tubes. Obviously, it gets pricey for the tooling when you're talking about such a large tube. Okay. So another question, just a quick one. Are we sharing the PowerPoint slide deck? Yes, we will share that in a PDF format. We can share that with everyone that is in attendance. And one final question, Kyle. Let's see. Just checking to see that there's no more questions coming in because we do have Adam. Okay. So a question from Adam regarding the different resins you mentioned. How can they affect drill out? Is one resin more cost effective versus another? I.e., if we had a low temp product with one resin and a high temp version that requires another, would there be a significant cost difference? So, talking about a couple things.
Right. As far as costs, yes, we do have different resin systems, and that's what we try to, depending on your need, that's what we would tailor the part and pricing off of. We have low temp resins. It's obviously going to be a lower cost, but then if you needed a resin system that was needing higher temperatures or higher pressure, that would typically be a higher cost. But yeah, we try to tailor what you're needing as far as the resin system. We don't want to try to offer you the primo package when all you're needing to achieve is like a 150 or 200 F temperature rating. We don't need to supply a 400 F temperature application, if that answers the question.
Yeah, in short, yes, there is a cost factor. It's not as significant as you might think, but the resins that go into the higher temperature, each time you go up a notch, let's just say, for example, if you wanted to buy a sheet of polyimide, and I'm not, we're talking sheet materials, but polyimide is an expensive resin, and it's got really high temperature performance, compared to a low temperature epoxy or standard epoxy. But yeah, if you're looking for a standard epoxy versus a higher temperature epoxy, you will pay a little bit of a premium to get the performance out of that. Okay, so I think we're gonna wrap this up, and I want to thank everyone one more time. Appreciate everybody for their attendance today and all the participation that we had. Again, please feel free to reach out to Kyle and I.
I believe our contact
info is right here, correct? And we'd be happy to answer any further questions. We'll answer any additional questions by email. Thank you, and have a great day.
Thanks, everyone.